When we learned about curved mirrors here over the last couple of days, we learned about two new equations that will describe mathematically these curved mirrors. We can draw ray diagrams, and we can make predictions as to what we're going to see for our image based on those ray diagrams, but it's difficult to be precise with those ray diagrams. General characteristics, yeah, great. But specific numbers for the height of an object or the magnification, the best way to do that is mathematically. Now, there are two new equations that describe that. The first one is called the mirror equation, and it goes like this. 1 over f is equal to 1 over dO plus 1 over di. And the second equation is the magnification equation. We say m is equal to hi over ho equals negative di over dO. What does f stand for? What does f stand for, Matt? No, the focal length, It's the distance from the mirror. Sometimes they say from the vertex of the mirror, but from the middle of the mirror, okay, to the focal point. Distance from the mirror to the focal point. And it's going to be measured in what units? Tell me what units we're usually going to use for focal length. It could be meters, yeah, it could be centimeters, it could be whatever you want, as long as you're consistent with all your other variables, right? As long as it measures a distance and as long as it's consistent, it doesn't really matter. Usually it ends up being centimeters, to be honest. DO stands for what? What's DO there, Maddie? Yeah, it's the object distance. This is from the object to the mirror. And the units for that are probably going to be centimeters as well, but whatever we use for focal length, that's what it would be. What about DI? Dylan, what about DI? Good. How far the image is away from the mirror. M is the magnification. It's the size of the image relative to the size of the object. It's a ratio, right? The ratio of the image height to the object height. Ratios divide. What units does a ratio always have? Any ratio, including magnification. None. Look, it's centimeters over centimeters. It's going to be no units. In biology class, when you're recording the magnification of your microscope, you would say it's maybe 400x, or you could just say 400. X isn't really a unit. It's telling us that it's a magnification, that it's times, 400 times the actual size of the object. What about HI? What does that stand for? Stefan? Yeah, it's how tall the image is, and it's going to be probably centimeters as well, although something different as long as you're consistent. HO is the object height. How tall is the object? And then, of course, we've got DI and DO. The only thing I'll caution you on right here is that little negative sign. That's important to keep the sign conventions correct. Let's talk about those sign conventions for a second. Positive and negative. When is F, DO, and DI, when are they going to be positive values? What's the word that goes with F, DO, and DI when we're talking about positive? Yep, see? Real. If F is real, then it's going to be a positive focal point. If DO is real, the object is real, then it's going to be a positive DO. If the image is real, it's going to be a positive DI. Now, the focal length is positive. It's a real focal point if it's a converging mirror. If it's a diverging mirror, then we get a virtual focal point, and therefore we'd make it a negative F. When do we get a positive DO? A real object, right? When do we get a real object? Always for us in physics 30. So we never have to worry about making DO a negative value. Not yet. Okay, if you're in first year university, then you might have a negative DO, but you're not going to have that in physics 30. What about DI? If you have a diverging mirror, the image produced is always virtual, so that'll always be a negative DI. If you have a converging mirror, then it's sometimes a virtual image, sometimes it's a real image. Out of the 10 ray diagrams we drew, 1 of them had no image, 3 of them had a real image, and 6 of them had a virtual image. So 60% of the time, it's going to be virtual. 30% of the time, it's going to be real. And 10% of the time, there's going to be no image. So listen, if you got to guess whether DI should be positive or negative, what are you going to guess? You're twice as likely to be correct if you guess it as being a negative value. It doesn't guarantee anything, right? We want to know when it's positive and negative, but if you have to guess negative, because that's the most likely correct guess. What about HI and HO? They're positive and negative not based on real or virtual, but rather based on, sorry, orientation, yeah, or sometimes we call it attitude, okay, which is right side up, upside down. If they're upright, then we'd make it a positive HI or positive HO. If they're inverted or upside down, we'd make them negative HI or negative HO. And finally, the one that doesn't really fit in this table, the one that doesn't really go with FDODI or HI and HO, in the spirit of Christmas with lights going on everywhere at night in Okotoks here now, let's make this one red. The magnification is positive when we have the image on the same side of the principal axis as the object. So in other words, if they're both upright, M is positive. But if they're both inverted, then M is positive. If they're both inverted, then M is positive because they're both on the same side of the principal axis. If one of them is upright and one of them is inverted, and it doesn't really matter which is which, then M would be negative. Usually, probably 99 times out of 100, M will be positive if the image is upright. But if the object was upside down, well, then the image has to be upside down for M to be positive. Once again, if you got to guess M is positive if the image is upright, even though it could be negative, but it's unlikely that your object would have been upside down to make that a negative M. All right? We had 5 questions for homework last night. I want to take a look at those questions now. Page 664. I'm pretty sure we're going to have to go over number 5 here. Is that correct? Any others besides number 5? 3? Okay, 2 and 3. Let's go over those 3 questions. And if you had a problem with one of the other questions, then I'll ask you to try it again, okay, because there's value in going back and trying something after we've gone over 3 more questions. If you still can't get it, then let me know. We're having a quiz on this stuff on Monday. Okay, quiz on Monday. No, quiz on Monday. Go home and try them if you're struggling with them. Okay, try them. Ask me questions tomorrow so that you can nail that quiz on Monday. Number 2 says determine the image distance, the magnification, and the attributes. Attributes are just the characteristics, right? Of a converging mirror with a focal length of 12 centimeters. Okay, I'm going to circle that because that makes a positive focal length. I want to find DI. I want to find M. I have a focal length of positive 12, an object distance of 6 centimeters. Okay, let's say 1 over F is equal to 1 over DO plus 1 over DI. 1 over 12 is equal to 1 over 6 plus 1 over DI. Let's figure this out on the calculator. Say 12x to the minus 1, subtract 6x to the minus 1. Remember, that's 1 over 12 minus 1 over 6. Press enter. And then let's flip that over. We get negative 12. So DI is equal to negative 12 there. Should be negative, 2 digits, negative 12. Now we want to find M. Let's say M is equal to negative DI over DO. Oh, that's a good one here. M is equal to negative 12 over 6. Is that right? What's wrong? Yeah, negative makes a positive, right? Positive 12 divided by 6 is 2.0. Now, that magnification technically doesn't tell me that it's a right side up image. It tells me that the image is on the same side of the principal axis as the object. But normally the object is right side up, therefore the image would be right side up as well. So what are we going to say here? Characteristics, it's upright, bigger or smaller, same size. Magnification is 2. It's twice as big. It's bigger. where it's larger? Is it real or virtual? Look at that table. Look at the table that we gave you yesterday that we just reviewed a minute ago. If you get a negative DI, what does that tell us? Negative DI. Okay, go up to the top of the table, go to the negative column, go down to where it says DI. What does it say in that cell? It's a virtual image. Negative DI means it's a virtual image. On the exam? Yeah, you know what? I know they give you everything in chemistry, right? Like they give you like a whole book in chemistry, but then they give you 1 page or 2 pages for physics. I wish they gave you that too. You get like what's in that 20-page book then? SRAs, I don't even know what that is. It's okay. That's okay. Question B here. B says we have a diverging mirror, focal length 5 centimeters. Diverging mirror, I want to circle that especially because that means focal length is negative. F is negative 5.0 centimeters. We have an object that's 10 centimeters from the mirror. We want to find DI and we want to find magnification. Let's say 1 over F is equal to 1 over DO plus 1 over DI. 1 over neg 5, be careful with the negative there. 1 over 10 plus 1 over DI. Let's do this one on our calculator as well. Let's say negative 5, x to the minus 1, subtract 10, x to the minus 1, flip it over, negative 3.33. Okay, centimeters. And then we'll say m is equal to negative di over do, negative 3.33 over do, which is 10. So what does that give me? Positive 0.333. Characteristics? Larger, smaller, same size. How do you know if the image is larger? Look at your table. The image is larger if the image is larger if magnification is bigger than 1, right? You don't even need your table for that, actually. The image is larger if m is bigger than 1. Okay, we got an m that's smaller than 1 here, so that means that we've got a smaller. Yeah, we've got a smaller image. Is it right side up or upside down? Positive magnification, assuming that the object is right side up, then the image is also right side up. And finally, DI is negative, which means the image is virtual. Okay, you know what? I'm going to leave you with C. Okay, it's the same thing, just a little bit more. I'm sorry? We'll do number 3 here. We'll do number 3 in just a second here, okay? But I'm going to leave C with you guys because C is very, very much like questions A and B. So give that a whirl if you have trouble with it. And then if you need help tomorrow, I'll help you out with it. Okay, let's take a look at number 3 though. It says a 5 centimeter high object, that's going to be HO. Place 2 centimeters in front of a converging mirror. That would be DO, and it's 2.0 centimeters. The image is magnified -4. So let's see, M is -4. Technically, that gives us 1 significant digit for our final answer, right? Yes, you're right the first time. Where does the image form? Where's DI? And what's the focal length? Okay, you know what? I'd love to use 1 over F is equal to 1 over DO plus 1 over DI. And I think ultimately I'm going to have to do that. But I need 2 variables to do that. And I don't have 2 right now. So let's try my other equation. Let's say M is equal to negative DI over DO. M is -4. negative di over 2. Negative 8 gives me negative di, so di would be positive 8, right? Where's the image form? 8 centimeters. What kind of object, sorry, what kind of image is this, by the way, if we get positive 8 centimeters for image distance? A positive image distance means it's a real image. We could, if we wanted to, project it onto a screen located 8 centimeters from the mirror. Okay, now let's find f. Say 1 over f is equal to 1 over do plus 1 over di. 1 over f is equal to 1 over 2 plus 1 over 8. This time we're not going to do any subtracting. 2x to the minus 1 plus 8x to the minus 1. Flip that over, 1.6. Good. Look at the value we got for f here. Not the number, but the sign of it. It worked out to be positive, right? Should we have expected that? Sure, we were told that it's a converging mirror. They didn't need to tell me it was a converging mirror because the math will tell me that, right? But you know what? It's a nice little check. I got a positive f. That means it's a real focal point. That means it's a converging mirror. Does that answer your question? Finally, number 5. This is kind of neat, actually. It's kind of tricky, though. A little bit more than what we usually see here. Light from a distant planet is incident on a converging mirror. The image of the planet forms on the screen 45 centimeters from the vertex of the mirror. So this is going to be di is 45.0 centimeters. I want to find the focal length and the characteristics. We don't have much given to us, right? We do kind of have something else given to us if we read between the lines. What's do? How far away is this planet? Do we know? No, but we know it's big, right? It's not 45 centimeters. Okay, it's a big number, like really, really big compared to 45 centimeters. Would you agree with that? All right, we want to find f, and let's try this. 1 over f is equal to 1 over do plus 1 over di. 1 over f is equal to 1 over big, whatever number that is, plus 1 over 45. What's 1 over 1? Okay, good, 1. What's 1 over 2? 0.5. What's 1 over 4? 0.25. What's 1 over 10? 0.1. What's 1 over 100? 0.01. Okay, and we're dealing with still 100 centimeters, right, which is a meter. What's 1 over, as that denominator gets bigger, that number gets tiny, like effectively 0. 1 over a number that's really, really big is basically 0. So 1 over f becomes equal to 1 over 45. So f becomes equal to 45.0 centimeters. That's it. Now, I want you to notice something here. Light traveling from a distant planet or from a distant star will go off in every which direction, right? Here's our telescope down here. It's a reflecting telescope. This ray of light misses the telescope. So does this one. So does this one. So does this one. The only rays of light that actually strike that telescope are the ones that are effectively parallel to each other. Agree? Because it's so far away. Okay? If they're not parallel to each other, pretty much parallel to each other, then they're never going to hit the mirror. They're going to miss it. What do we know about rays that are parallel to the principal axis? That's right, they never touch, but they'll reflect through the focal point. Now, even if these rays aren't parallel to the principal axis, but they're parallel to each other, then they'll still reflect and converge below the focal point. or above the focal point, depending upon which direction they're coming from. So the focal length will still be the same as the image distance, even though it's not going to be right smack on the focal point. And that's what we saw right here, right? We saw that when we calculated this, our image distance was 45. Our focal length was 45. Why? Because the rays coming from this planet are parallel to each other. What about the image characteristics here? Boy, we know it's real. Sorry, second here. Forms on a screen, so we know it's real. Right? What else do we know here? Let's say m is equal to negative di over do. Di was 45. Do was big. Magnification is going to be what? Small, right? So we know that the image is going to be formed smaller than the object. That doesn't make sense, does it? In a telescope, don't you form an image that's bigger? Don't you magnify it? Think about that for a second before you answer.
Up close they magnify.
That would be a microscope, right?
So a telescope.
Surface telescope and a microscope. No, seriously, if you're looking at a distant planet through a telescope, it doesn't magnify it at all.
Which brings it.
The image that you see is it magnifies what you would normally see if you look in the sky. But the image that you see of the actual planet is going to be much smaller than the actual planet. If I look off in a telescope at Saturn and I can see the rings of Saturn, then you can't tell me that the image I'm looking at is bigger than the actual planet. That would be a really small planet if the actual object was smaller than the image that you see. Having said that, when you look up in the sky and see the moon, obviously it looks to be much smaller than it really is. When you look in a telescope, it looks bigger than it does with the naked eye, but it's smaller than the actual object. Does that make sense? So we'd say our characteristics here are, first of all, that it's real, it's projected onto a screen, it's smaller because the magnification is less than 1, and the magnification would also be negative value, so the image would be inverted. The image is upside down. But you know what? It doesn't matter. You're looking at a planet, right? Who cares if it's upside down or right side up? There isn't even really any upside down, right? On Earth there is, but you're looking at something in space. There is no up and down. You guys good there? All right, what I would like you to do tonight, and you guys are probably going to have a little bit of time towards the end of class to do this because you guys are a little bit ahead of the other one here. I'd like you to work on 5 questions on page 665, questions 7 to 11. We'll go back to that a little bit later in class if we have time.